YouTube? Good?
Yeah,
Okay.
I'm good.
Okay, we should now be live. Yeah.
Good. Okay, so welcome to the second day of PEPM, and we start with a session with an invited talk by Matúš Tejiščák. I hope it's approximately how it should be pronounced. He'll talk about Erasure in independently typed programming. Matúš is a fairly recent PhD graduate from the University of St. Andrews in Scotland, and his interests are mainly compilers, dependent types, and type erasure. He's currently working on at a company called Cordify, which makes e-learning software for learning to play music, as far as I could gather. So we hope, I'm not exactly sure what dependently typed programming has to do with that, but regardless, let's welcome Matúš, and please go ahead, Matúš.
Well, thank you, Torben, very much for the introduction, and thanks everyone else for coming. And as announced, I'd like to say something Erasure and dependent types. So here's a program that contains a data definition of natural numbers, unary natural numbers, with a zero constructor and successor constructor, as we see in as is usually in dependently typed languages. This particular program is written in Idris, in the Idris syntax, but that doesn't really matter. It could as well be written in Agda or Coq or something else. It contains the type of unary numbers, but unary numbers are easy to reason about, but they are quite inefficient because they are unary. So we could also define a type of binary numbers, which are more efficient, have a logarithmic size compared to the unary numbers. And in order to be sure that the program does what we want it to have it correct by construction, we index those binary numbers by the corresponding unary numbers, that by the value, by the unary value of the binary number. And then the program contains two further functions. One is called add1, that takes a binary number that represents n and returns a binary number that represents a successor of the number. And thanks to the index, this function has to compute the successor of the number. So the function must be correct by construction. And then we also have a function read bin, which is an IO action that returns a binary number from the input. Then below the line, there's a program that reads a binary number using the function read bin, adds one to it, and prints the result to the output. And without seeing how the functions add one, read bin, or anything else are implemented, you can tell that this program will run in exponential time and space with respect to the number of bits in the binary number, unless your compiler does something clever, and that's what I would like to talk about today. So where does the exponential behavior come from? Well, it was not visible in the previous slide, but if you include implicit in program, if you elaborate the program, which is the compute, it has to elaborate implicit numbers. You can see that the constructors I and O contain an extra implicit field that contains the unary representation of about half the binary number, which is exponentially sized. This is also visible in the function add1, which also has to take the unary representation of the number it takes. And any arithmetic that you perform on those binary numbers, we'll need to perform the equivalent operation on the unary numbers in order to keep the indices and the binary numbers in sync. So if we look at the memory layout of of a binary number represented this way, there's a string of bits on the left in black, which are actually the interesting bits. That's the ones and zeros of the number. These are the bits that we use to that we compute with, that the program looks at runtime. And then on the right, there's lots of memory taken by the implicit parameters that are there as evidence to the compiler that the program makes sense, but they are not used at runtime. These implicits are not necessary for computation. So in this talk, I'd like to convince you that this is a real problem, that it is not acceptable to have a binary number adder run in exponential time. Because what we just do is that we gave more information to the compiler. If we didn't include the indices, the program would run in linear time as expected. But we give more information to the compiler, and that makes our program run slower. That's really bad. So by saying more about the program, we should not make it run slower. Therefore, we need to erase all that runtime, all that compile time only information from the program before running it. There are ways of achieving erasure indirectly that some programming languages use, such as compile time irrelevance or proof universes, that have erasure as consequence. However, since they do not address erasure directly, but it's just a consequence of that other thing, it also inherits the restrictions and limitations of that other thing, which means in practice that you cannot reasonably erase what you would like to erase. Therefore, there is a phase distinction in dependently typed programs between things that are useful for runtime and things that are not. And I'll illustrate that there is a way to efficiently approximate that phase distinction, which is more useful than approximating with let's say, the prop universe. I also illustrate that that erasure makes other optimizations more powerful, and that it also makes the compiler run faster because there's less code to generate, and it's just faster. So one way to achieve erasure in a language like Coq would be using the prop universe, which is the universe of proofs designated for erasure. Above the line, you can see an attempt to write a program in syntax. Again, it just doesn't have prop, but I have. And because you want to raise the number n, the indices of constructors I and O, you create a type n prop, which is natural numbers, the same as regular natural numbers, except that they are in prop instead of set. And you use that type to define the indices of I and O. This kind of approach works well for proofs. If you have a record that contains a list and it contains a proof that all elements of those of that list are distinct, that proof is erased, the list is kept, everything's fine. However, this doesn't work that well for indices. So if you have a function like nat to bin that takes a natural number and returns a binary number corresponding to that natural number, then there's a question, should n be in prop or not? Clearly, nat to bin needs to look at n to do its job. So n must not be erased, but bin takes an erased number. It takes a number which is in n prop. So there's a contradiction there, and cannot be both things at the same time. Furthermore, this suggests that maybe you have to duplicate every data type in prop and not in prop, which is wasteful. And also there's a question of what does it mean if a function returns an erased value? Are you ever supposed to evaluate that function at runtime? Does it make sense? Some of these questions are answered by an embedding that people have worked with, namely the erased monad, that embeds sets into prop and lets us write nat to bin in the way that we can see, where it takes a non-erased n, and the index of bin is an erased n. But then you get issues with equality. You would like to have a theorem or function, or you would like to know that if two erased values are equal, then the non-erased values are equal as well. And the conversion functions get in the way. So equality gets difficult, and it turns out that you actually have to state this in an axiom. If erased went from type to prop, that axiom is known to be unsound. So it has to be from set to prop, and it probably requires a predicative set as well. So there are some restrictions that come with this sort of encoding. While it addresses some shortcomings of prop, it does not really address all of them. Another traditional way of achieving erasure is irrelevance. And by irrelevance, I mean compile time irrelevance, or rather the property of subterms being ignored in definitional equality. Unfortunately, the terminology is quite confused in the literature, because the word irrelevance alone could mean irrelevance at compile time, which affects equality, but some authors also use it in the meaning of irrelevance at the runtime irrelevance, which I call just erasure. So in the next slides, I will say irrelevant for compile time irrelevance and erasure for runtime irrelevance, which does not affect equality. So Agda has irrelevance or compile time irrelevance traditionally, where you can see, which you can see in the following data declaration. Tiny dots in front of the sign before the braces in the constructors. That marks those values as irrelevant because we want to erase them. However, because the argument of bin is irrelevant as well, then n, the empty binary number, which is meant to correspond to 0, type checks as bin k for any k, because k is irrelevant, k is ignored. That's too much. That erasure or irrelevance erases too much. It erases even before type checking, before conversion checking. However, if you wanted to have bin with a relevant argument and I and O with irrelevant arguments, this would not type check in Agda with the traditional notion of irrelevance. Later on, Agda got shape irrelevance, which lets you use irrelevant fields of constructors, data constructors, but with relevant fields of type constructors in some cases. And recently it even got runtime irrelevance, which is the notion of irrelevance I'm talking about today. So besides causing issues in some languages where irrelevance is too powerful, inference of irrelevance is harder than inference of just erasure, because type correctness depends on what is irrelevant, what is not. So you cannot tell whether the following judgment n has type bin 42 holds or not, because unless you know whether the argument of bin is relevant or not. That said, there are languages that use irrelevance, such as Zombie or ICC, or the calculi that use irrelevance, where irrelevance does not cause the kind of problems as in Agda, because they use untyped equality. And in these languages, the problems with you can define the family of binary numbers, but still you have the question of inference. As an experiment, or as one way of trying to address the question of erasure, in the past, idris tried to make implicits lazy to avoid evaluating them if we didn't need them at runtime. However, laziness is a dynamic check, and the fact whether we want to erase something or not is a static property. And laziness being a dynamic check is, first of all, the overhead is still there. So all the code and all the computation is still present in the program. It just may or may not be triggered, and you do not know at compile time whether or not it will be triggered, because it's computed at runtime, and therefore it's unstable. You have no guarantee at compile time whether something will or will not be evaluated. Besides, laziness is not powerful enough. If you look at the function that calculates vector length, that takes a number and a vector with that length and returns the counts the const cells in that vector. In the second clause of the function vector length, we not only match on the number n, but we also pass the projected value n into the recursive call. While erasure, while a dedicated erasure procedure can spot that n is unused in the recursive, it also laziness would not help us with that. And finally, if you have a recursive function that doubles its first argument for whatever reason on every iteration, then you have a choice. If you never evaluate first argument, it will just accumulate chunks inside its first argument, causing linearly sized but still a memory leak. However, if you ever force the first argument of this function, then it will calculate an exponentially sized unary number, and it will just exponentially blow up. So you have a choice between a memory leak or an exponential blow up. While with Erasure, if you erase that that argument, then this is gone completely, and none of that would happen. Finally, there's some simple approaches to Erasure, such as erase exactly the types. We've already seen that this doesn't really work very well, because in the function add1, we want to erase the n, which is a natural number, which is a unary natural number. That's clearly not a type. Therefore, I talk about erasure, not about type erasure, because we want to erase things that are not types, not necessarily types. And we might want to retain types for runtime as well. Then another approach could be erase exactly the implicit, but that doesn't work very well either, because if you want to have the operator of text concatenation that for some reason requires the encoding of the text to be known, then the implicit needs to be present at runtime. It is implicit to have a nice behavior, nice syntactic behavior of binary operator, but in fact it's a runtime relevant thing. More generally, Conor McBride came up with something he called the Hindley-Milliner coincidence, where the distinction between types and terms, between the implicit and explicit parts of programs, between the inferred and the programmer given, dependently quantified, non-dependently quantified, parametrically quantified, non-parametrically quantified, and erased and unerased tend to coincide in language like Haskell. But this coincidence is no longer useful in a dependently typed language, because sometimes we want to erase something that is not a type, or we want to give types explicitly, or we want to infer terms, we want to infer whole programs. And so this coincidence breaks down, and basing erasure on it is probably not a good idea. So what do we do then? How can we identify the phase distinction between what can be erased, what should not be erased? Well, let's have a look. I'll give a brief example illustration on the vector length function. Here we have a function that counts consists in a vector, and returns a number, and we would like to see what we can erase in this function. So the first step is to elaborate this function, which means write out all the implicits and everything that actually goes on behind the scenes. So we added some curly brackets, some extra indices, and an interesting thing happened on the left-hand side of the pattern clauses. So the first pattern clause contains Z in square brackets. That square bracket, if you have looked at the vector and you have seen that it's a nil, then you know from the type correctness of the program that the corresponding index n will be 0. It must be constructor Z. So you don't need to look at it. Similarly, when you look at const, you know that the index has to be a successor, has to have a successor shape, and therefore you also don't need to look at the constructor tag of the successor. You might say that this is actually an explicit annotation of erasure, or you can erase anything that's in square brackets, but that's not entirely true. Well, actually, that's not true at all, because the square brackets do not tell you what you erase. The square brackets tell you, or tell the program, what it should look at, and erasure is then a consequence of the chosen operational behavior. So, for example, it would be perfectly fine to look at the index n and erase or force the vector. So if you look at the index and you know it's z, then you know for sure that the vector has to be a nil. And if you look at the index and it's a successor, you know that the vector has to be a cont. So it's up to the programmer to choose the operational behavior, what the function should look at, and then erasure follows from that. Furthermore, there's more things than just those that are in square brackets that will be erased here, and some things in square brackets will not be erased. So once we elaborated the program, we need to add some more detail, namely pattern variables, which are the two blue lines. We add explicit binders for pattern variables, and I put them in between the left-hand side and the right-hand side of every pattern clause because of the information flow. The information flows from the pattern through the binders into the right-hand side. So in the first clause, we bind just A. In the second clause, we bind 4 variables, of which X is not used on the right-hand side. The next step is to number every single column in the program, every single variable binder in the program, and every single application in the program. We just give a unique number to each of them. There's a small trick I pulled here. If you look at the constructor cons, its argument x is explicitly annotated as r. That's to prevent erasure from erasing it. Because this is a very small program, the erasure inferred from it alone would erase even the elements of the vector because they are not used anywhere, and that would lead to a program that's erasure optimal but not very instructive. Vectors would erase to something isomorphic to natural numbers. So I manually marked x as used, as it would be in a larger program. Usage of x would come from the context. So once we numbered all the columns and all the applications, then we can look at some constraints or at some observations that we can make about this program. So for example, if we look at the red bits, the column number 19 and the application number 30, we can see that column number 19 says that gives the erasure annotation for the first argument of the function vlen. And because application number 30 is the first argument, must be the same as the annotation in place 30, because it's the same function. Therefore, we can make the observation that retention number 30, or retention annotation number 30, equals to retention annotation number 19. I say retention annotations because I use retention as opposite of erasure. And eventually all these numbers will be replaced by a retention or erasure annotations. So since R30 equals R19, we can encode that in a horn clause form as R30 implies R19 and R19 implies R30. So the retention annotations behave like Booleans, saying whether this particular thing that is annotated should be retained for runtime. Another observation that we can make is on the right-hand side of the second pattern clause, the blue bits. Here we can observe that the variable n is nested under two, is used under two nested applications, application number 46 and then application number 44. If, for example, number 44 is erased, then the whole frame is unnecessary for runtime, and therefore n could be erased as well. If number 46 is erased, then n could be erased as well. But if number 44 and 46 are retained, then n has to be retained as well for the application, for the program to work. We encode that as a constraint that we can see in the second line of the table, saying if R44 and R46 is retained, then R39 has to be retained as well. R39 is the annotation of n at its binder. So it's the second, it's the pattern variables in the second clause. So that gives us a constraint on how much we can erase 39 based on whether or not we erase 44 and 46. But there's constraint from the other side as well. That's the green constraint. We can see that in the pattern, n comes from a place that's under two applications again. And if n is retained, then both of those applications have to be retained. Because if, let's say, application number 31 is erased, then n would not be available. Therefore, the retention of n implies retention of 32 and 31. So in patterns, retention works the other way around. I mean, formally, the constraints look the other way around as then on the right-hand side. In horn clause form, this is also expressible as horn clauses. We express it as two horn clauses that we can see in the third line of the table. So the retention of 39 implies a retention of both. This way, we can go through the whole program and collect constraints like this. We collect horn clause shaped programs, which is good because we can solve them efficiently. And we find a solution that has least number of retained values. And having that solution, we can substitute the solution into the original program. In which every part of the retained all parts of the program that are marked as erasable. Arriving at the program that looks like something that that Haskell programmer would write. There are no traces of dependent typing in this program. Of course, we can erase a lot If we erase the whole program, then we will get something that runs really fast, but that's not very useful. So it's actually, there's a proof that this erasure procedure commutes with reduction. So if you have a term t, and you reduce it one step and then erase the result, or you first erase t, then you can reduce the erased version of t to get the same result. If you have a calculus that confluence, then and subject reduction, then this holds for multi-step reduction as well, which is especially interesting in the case shown in the diagram below. If the erased version of t is the same, such as which is the case for numbers, strings, booleans, and things like that, then the erased program will reduce, the erased term will reduce to exactly the same term, assuming confluence and subject reduction. There are further benefits to erasure. Erasure makes, one of the things is that erasure makes the new type optimizations more powerful. The new type optimization is an optimization that takes a data type that contains exactly one constructor with exactly one field, and represents it at runtime as that field alone. So it removes the extra constructor wrapper, making everything a little bit more efficient. Erasure makes this more powerful because you can perform new type optimization after erasure. So for example, this data type t, where the index n is erased, can also undergo new type optimization because it has only one unerased component, which is the binary number itself. So this way, complicated structures with lots of indexing and lots of nesting can actually be erased and new type optimized into the bare bones representation of what we want to compete with. Another thing that erasure helps with is the identity optimization, which is an optimization that spots identity functions, such as the weekend function on fins. The weekend function looks a little bit complicated when it's not erased, but once you erase it, then you can see that the erased version of the weekend function is an identity on the representation of the fins. And therefore, all its applications can be removed and can be replaced by the argument directly, removing yet other overhead. Another optimization that's enabled by erasure is the NAT optimization, which is found in Idris and compiles natural numbers into big integers, which removes a little bit of, makes them a bit more, especially memory efficient. The optimization doesn't change the complexity very much, but it helps with overhead. However, especially interesting with data types like elem, which is a proof of membership of an element in the list, if you wish. But after erasure, it turns out that elem is isomorphic to natural numbers, and this can be also compiled down to a big integer. So we can compile proofs of membership to just indices or numeric indices in the list. Finally, with sufficiently clever erasure, we can match on erased data. So, for example, the subst function takes a proof of quality of two values and then coerces px to py. Because the constructor tag is forced on the left-hand side, because refl is the only constructor, and its only implicit argument is not used on the right-hand side, the whole argument can be erased, leaving subst to be an identity function that can later be removed by the identity optimization. So all these optimizations work together to remove, to cascade and remove a lot of overhead. Of course, for this kind of matching on erased data becomes a little bit problematic if you have non-termination, if you can have absurd assumptions and things like that. So this also needs more care. Erasure also makes the compiler run faster. So even though it does take some time, it saves a lot of time in the code generation stage. This is the plot we're seeing is the measurement that I did with my implementation of Erasure, which compiled a dependently typed program into chicken scheme and then ran chicken scheme to obtain native code. This contains just the compile time stage, including type checking time, erasure time, and code generation time, which was done by chicken. And we can see three programs. One is palindrome checker. The second one is binary number adder, which is similar to what we have seen. And the third one is run length encoder. And all of them show a lot of improvement in the compile time because there's simply less code to generate. The code has been erased and chicken has less work to do. So there's a lot of other things that we could do with Erasure that we are not doing yet. There's some things that have been implemented in Idris, and there are some things that are being worked on and that are future work, such as inference of irrelevance. It turns out that we can infer irrelevance if we split the type checking stage a little bit. First, we type check the program producing the erasure or irrelevance constraints, but we do not perform any conversion checks. Then we solve the erasure constraints, obtaining information what should be erased and what should not be erased, and then run conversion checks only on the data that is not erased. So effectively, we make all erased things also irrelevant at compile time. This seems to work, but requires more work and more theoretical work. We can interpret is the inference of procedure can also infer linearity. It's a little bit pushing it. So if you just use this procedure that I sketched, pretty much unchanged, it's just you change the constraints from being logical to arithmetic, and use a constraint solver to solve them. You can infer a linearity with the drawback that it takes quite a long time, even for small programs. So it may or may not be practical, but this is something that we can do with this simple way of gathering constraints and solving them. And of course, it would be good to actually express or reformulate the algorithm, generalize it for any partially ordered summary of quantities, as is a recent movement in the literature. Another thing that's that would be useful to do, useful to have, is erasure polymorphism of functions. So if you look at apply, this is a function that when applied to a constant function that does not use its first argument, we would like to preserve this knowledge. So apply lambda x42 should be inferred as a function with an erased argument. On the other hand, apply identity should be inferred as a function with a runtime argument. Also, for convenience, a function like map should work with either version of the function it's given. So this seems to be a necessary feature, especially when you throw linearity into the mix. That would be good to extend the work in, and we can infer erasure polymorphic signatures, but that would need some more work as well. Further open questions or things that would be useful to have is erasure polymorphism of data as opposed to erasure polymorphism of functions, which can be illustrated on the case of dependent pairs. Usually, dependent pairs are used in three different ways. One is just a pair, such as in a vector or a pair of numbers, coordinates. Another way of using a dependent pair is to have a number paired with a proof that the number is even. In this case, we want to keep the number for runtime, and the proof is something for compile time, but we probably don't want to compute with it, and we want to erase it. And the third version of dependent pairs that is used is a dependent pair of an index n and a binary number that represents n. In which case we probably want to erase the n, but we do not want to erase the binary number. Unfortunately, at the moment, in interest, we have three different types for dependent pairs. Also, Coq has sigma and exists, and these types of dependent pairs are just distinct. It would be nice if the compiler could figure this out for us and erase dependent pairs the way we need. Another open question is separate compilation, or maybe it's more an ergonomy question. Erasure doesn't need recommendations to do its work. However, module B. If you look at module A, which contains a definition of data type T with a constructor and a function f, and you ask, can we erase the first argument of f? The answer is actually not clear. You cannot tell by just looking at A. because if you add a module B that reads from the first field of the constructor, then F has to erase, F has to retain its first argument. However, if you have no such module and the field of C is never read, is never accessed, then you can erase the first argument of F. This is similar to a problem in Haskell or ML, where you do not write top-level type signatures. If they make a mistake in some functions, the system infers the wrong type and breaks something else far away from the place where you actually made the mistake. So this is probably too much inference, and it seems that the best answer to that is explicitly annotating data types and having everything else inferred, so that this action at distance doesn't happen. So to conclude, there's a phase distinction independently typed programs, but the distinction does not coincide with the usual division between terms and types, and implicit and explicit. This phase distinction needs to be identified if we're serious about writing dependently typed programs in the way we want to, rather than being forced by the system to use external proofs as opposed to structures correct by construction. So we have to address this program. Fortunately, there is a useful and efficiently computable approximation of this phase distinction, which I called erasure inference, which does not have the drawbacks of modeling erasure indirectly via prop or compile type irrelevance. And erasure makes other optimizations more powerful and makes the compiler more efficient. So that's definitely a good thing, I would say. So thank you for your attention. And if you have any questions, please go.
Yeah, thank you. So let's all clap our hands. Yeah. So any questions? You can just speak up. I think if two do it at the same time, we'll find a solution. So just speak up if you have a question. You can
I
also
have a question.
Good. Then speak up.
Okay. So very nice talk, Matúš. This is great work.
Okay.
The way I think you're presenting this is as kind of an analysis you do as part of compilation, but towards the end you're alluding to these problems of separate compilation and modules and so on, and polymorphism over erasability, and that's all suggesting that you would actually want to expose whether something's erasable actually in your source language as a type annotation or something. That's not something you've actually implemented yet, is it, in Idris, or is it?
No, we have no erasure polymorphism, so we do not have explicit erasure variables.
You don't have, yeah, because it strikes me that another problem you might run into, just as well as we often do when we have sophisticated inference procedures, is unpredictability. So this is actually related to the talk, the keynote we had yesterday from Julia Lewall, where she was saying how important it is to be predictable. And I wonder how whether you've observed that in practice being a problem, or it looks like it might be, in that you have a program, you maybe think oh yeah, these things are probably going to get erased. Maybe you just change it slightly, and then suddenly something doesn't get erased that you were relying on, and your performance collapses. Have you observed that problem? And
Yes, so we did observe that problem in Idris 1, where Erasure was indeed fully inferred, and you had almost no influence on what would be erased, and that's exactly what happened there.
Edwin, I see, says, I have observed this when implementing Idris 2.
Yes, exactly. So there's you discover things that you make a mistake. It's not it's not obvious, and things that you would expect to be erased don't get erased.
I mean, it strikes me that the right solution when you have this kind of problem is exactly to make this thing explicit. So if you really care, this thing must be erased, then you must be able to sort of say that in your source language.
Yes. So we need to strike this balance that I described between convenience, because you also don't want to put erasure annotations everywhere on every column and every application, but you also want to have, if you want to have the control, I want this erased because it's too big, it's exponentially big, then you should have the ability to do it. So yes, I agree with you on that.
Thanks.
Any further questions or comments?
Yeah, I have a question. So I was surprised to see the annotations on application nodes. Why do we need them? I guess I would expect that since the functions that you're calling sort of at the head of the chain of applications have known types, that we could just use the same annotations. Maybe it sort of boils down to the same thing, and I'm just sort of doing some small optimization. But I was wondering if there was sometimes where you couldn't do that.
Right. Indeed, annotations are more. They make the formulations neater. Make the formulation neater. So, if, for example, in the erasure procedure, when you removed everything that's annotated with E, you need to also remove applications that are erased. Now, if you have those annotations in applications, then you have that information right there, and you just recurse through the AST and you remove what you need to remove, and that's done. If you do not have those applications there, then you would have to erase the program by type checking it again and matching up all those types and matching up all those pi types with the arguments again, which is more complicated.
Any other questions?
I had another question. So yeah, very nice talk again. And
thank you.
So my question is: so it seems that your analysis is based purely on whether a certain argument is used somewhere in the program or not.
Mm-hmm.
And I was wondering whether you could also mix in some extra information that you get from the types of your arguments. So for example, you could determine that arguments of a certain type, because it's a singleton type or an empty type, or I mean, some other type that can always be erased. So did you consider that? And could you integrate
yes.
that with your approach?
Yes, you can. It's on the slide. If I go with the slides back, let me see. Oh, here, it's the second bullet point is matching of erased data, and
right, but that only works when you actually match on the data. I was thinking of something that just looks at the type that would be able to erase an inequality proof even if you don't match on it. Just because that's the type with a single constructor.
I have not considered erasing things just by by the type they have.
Okay.
This procedure that I described works on how variables are used, not what
Right.
type they have.
Yeah, yeah.
So if you didn't if you didn't match on the proof, then it would be unused because it doesn't appear on the right hand side. So it would be erased anyway.
Right, but I mean that is also related to the question of how modular this approach is, because the way you formulate it is really as a whole program analysis. And if you want to apply the analysis in a more local way, then you might have a function that comes from another module that takes an equality proof. And then you couldn't infer whether it's using this argument or not.
Right, so if you, the analysis needs to be a whole program analysis if you want to infer the erasure patterns of data constructors. So as I have illustrated in the, where is it? Oh, here. In the separate compilation bullet point, the problem here is that the action at distance that the type of constructor C is not annotated, and therefore what happens in module B can affect what happens in module A, and this needs a whole program analysis. However, if C were explicitly annotated, let's say N has to be retained, then whatever happens, you can proceed function by function and erase types, infer erasure per function.
But that doesn't seem enough in general, because I might be programming against some abstract interface with some functions in it, and I don't know whether those will, I mean, the arguments of those functions will be erased or not. I mean, that depends on the implementation of that interface.
Exactly. So in that case, this is similar to using foreign function interface or similar things, where you have to explicitly say that what is erased and what is not erased.
Okay. Then okay, you have to.
Or you have to use erasure. If you had erasure polymorphism, you could probably express what is some relationships between erasure variables.
Right. Yeah, I mean, I think I agree that if you really want to make this practical, we need some way to express erasure's polymorphism. Yeah, but yeah.
Yeah. So yes, and with erasure polymorphism, my dissertation describes one way of doing it, and that way bundles the type signature of a function with constraints that relate the erasure annotations in the type. So the type of a function is no longer the type term that describes the type, but it also includes the relationships between the types. It's just constraints. It's a bag of constraints or a set of constraints between the annotations. And once you start thinking about type signatures as consisting of a type and constraints between erasure annotations, then it becomes more modular again. You do not need to look inside of the function because you have the relationships between the erasure variables captured by those constraints.
Yeah. Okay, yeah, thanks. It's interesting.
Yeah, there is one question from Sam. We can maybe take that quickly, but let's that be the last question.
It's not from me. This is copied and pasted from YouTube. So someone called IDGUI. I don't know how to pronounce the name, but you can read it in the chat anyway. Erasure seems to change the arity of functions. How do you deal with higher order functions and the partial application of functions whose arity has now changed?
Sorry, could you repeat the question? I couldn't hear. I think you're muted.
Yeah, sorry, I'm just reading out what they wrote. It says, Erasure seems to change the arity of functions. How do you deal with higher order functions and the partial application of functions whose arity has now changed?
Right. That's an interesting question, and the answer is relatively boring for this system where you do not have erasure polymorphism, because the arity is indeed different, but it's still fixed. So a function that used to have 5 arguments will have 2 arguments now, but it's still 2 arguments in all places in the program. However, with something like erasure polymorphism, this would have to be addressed as well. One way of addressing it is actually passing dummy values instead of erased values. So not changing the arity of functions, but just passing nulls, which happens to be what Idris 1 used to do. So that's one way of addressing that question.
Yeah, so let's thank the speaker again. And we have the next session in 23 minutes now. And remember that it uses a different Zoom room than this one. So remember to open with the new Zoom room address. You can find that in Clouder.
And I guess in the meantime, if you want to ask further questions of Matúš or discuss things, you can attempt to meet in Clouder or ask questions in the PEPM room in Clouder.
Yeah. So see you in 23 minutes. Bye.